Can you all hear me? Awesome. So I'm Dave, I'm from Sajari. And just by way of introduction, I just want to quickly tell you what Sajari is and what we do. So Sajari is a startup based in Sydney. We build machine learning based search technology. So essentially a self-learning search index. It's all built in-house, right down to the binary encoding of data on disk. You're going to hear more from, well, something similar. Our encoding is slightly different, but from Manish later. All of the stuff, because we're doing it ourselves, it's a different approach to Lucene, which you might have heard of, powers things like Elasticsearch and Solr. Everybody says, oh, you do search just like Elasticsearch. Well, actually, what we do is slightly different. We had slightly different goals. So all of our stuff is designed specifically to run on Google Cloud and AWS. And all of it runs actually in Kubernetes, so a Kubernetes-style environment. So everything is in containers. We use gRPC to communicate between them. And it's all written in Go, I should say that. So in terms of the search index, we take ordinary queries that you might expect from a search engine. So keyword queries, we go Meetup, like prioritizing results based on locality, boosting popular items, recent items, all this stuff you've probably seen before. What makes us more unique is that actually our index is self-optimizing, as I mentioned earlier. So the ranking algorithm optimizes searches on an individual search level. If you've ever actually tried to configure a search engine from scratch, it's really, really hard, because what you essentially have are lots of big levers that you're pulling to try and optimize specific queries, because specific words have meanings in the context that you're looking at. And so you pull one lever and it makes one search term produce the results you want, but it throws off everything else. And you basically keep doing this and tuning it until everybody stops complaining that their particular search thing they want, you know, it's now showing the thing they need. And then, yeah, you go home after all of this pain. And yeah, inevitably it starts again. One of the other things that we do is a lot of feature extraction for queries and documents. Not just for documents going in the system, that is, but for queries as well. So obviously things like spelling correction, autocomplete, pretty standard. Synonyms based on things you would program in, so like IoT, Internet of Things. But also model-based stuff using things like Word2Vec, if you've heard of that. We also do a lot of classification of queries into categories. Is this, you know, is it a question about, that's a support question, or is it something about a product, like how much does this cost? Or is it an event, like where is this thing? When is it on? Stuff like that. And we also apply that to documents coming into the system when we're indexing them, so that we can then better match those kinds of queries to those documents. There's all sorts of other stuff we do as well, obviously, on documents, passing standard metadata out so that we can use that in the matching. So, you know, locations, dates, names, everything. When we're doing web crawling, one of our services is to do web search. So we have a lot of stuff specializing in, you know, parsing HTML, open graph tags, stuff like that. And like down to the lowest possible level is you take a document that you're putting into your search index and you just turn it into a huge long vector, which you then do a whole chunk of machine learning on to like work magic, essentially, when you're trying to find a good match. So why are we interested in storage? Well, all of the stuff I've been talking about involves a lot of moving data around. Throughout our systems, we had a lot of code that was pulling files from everywhere, from S3, like from the local machine, from like Google Cloud Storage, and it was all a huge mess. All of the implementations were inconsistent, just by definition, and a lot of them actually, the logic in the programs themselves were based heavily on what the library had defined was the usage pattern of the particular calls they had. So like, for instance, I think like S3, there are about 3 or 4 libraries you can use, and we were using like at least 2 of them. So all of the stuff was a pain. We need to fix this. So what we want is a standardized storage layer. And it needs to be so simple that you don't spend any time worrying about it. You just ask for data, you get it back. When you're building a system which is going to be using data, pulling data, you don't want to spend time messing around having to test this stuff. You want to be able to quickly prototype stuff and then move it into production without changing any code. Obviously, it needs to work with all of these storage providers that I've previously mentioned, and you need to be able to easily add new storage providers. So let's just dive straight in and see what it's like to fetch a file in its entirety from a few different systems and see if we can see like a way that we could generalize this. So this is read from local. This is a dumb function, but essentially it just reads a file from the system using os.open. I hope everybody's seen this before. Even if you're new to Go, this hopefully is like the first thing you do, or at least nearly the first thing. And then we just read the whole thing and return it in a byte slice. So this is really easy. So now let's try something a bit more complicated. Google Cloud Storage. Okay, so read from GCS. So instead of the path, we also need a bucket, because that's how file systems are segmented in Google Cloud Storage. So this is looking a little bit different immediately. Plus, we've got all these credentials and stuff and a client we have to construct. But actually, what it comes down to is we get this reader object here, which we can read the data from again, just as we did from the file. And then obviously, we close it and tidy up. And we're good to go. We've got our data. Amazon, very similar again. Again, you've got things like region, authentication credentials, and the bucket as well. They have a bucket system as well. Well, I'm sure you know this anyway. But again, you can construct the calls using your library of choice. There are many of them. And you end up with a reader, which you just read from, and then you close at your leisure, or like depending on how careful you're being about resources. And then you get your byte slice of data back. Okay, so it's pretty obvious from that quick like dash into manically creating implementations for every platform you can think of. What we have here is an IO read closer, and we can now focus on that to generalize everything. So let's create an interface. It's very simple. Let's call it FS because we don't like to type. And it has one method, which is open. It takes a path. It returns an IO read closer that you're going to read data from, and then you're going to close it. So it's the responsibility, and this is like important as well, it's the responsibility of the caller who gets that read closer to close it to ensure that all the resources that you're using in order to access that, be it a network, be it the local file handle, are released back into the system. And it can also return an error if like something balked along the way. All right, so what does this look like? Well, it's pretty simple for local, as you would expect. We have a local object and we just stick an open method on it. So hopefully no complaints there, no questions. Using it is a little bit different, but it's very easy to get used to. So it's local, and then the local root that you want to use as the base of your file system, and then you can just call open on that. Pretty straightforward. All right, so what does Google Cloud Storage look like? Well, actually, it's exactly the same. If you remember, we had a path and a bucket. So now the bucket is the thing that we need to hold in state for that particular system. And then we just define our open method, which takes the path and returns an IO read closer. So we have all of these calls to do the credentials and the client, but actually in the end, it's still this read closer. And so to fetch a file now from a bucket instead of the local system, we initialize cloud storage with the bucket name and call open on it. S3, pretty much the same. It's a bit more complicated because of the region and the auth again, but we've got this method, pretty straightforward to implement. You get a read closer. Great, this is awesome. We're moving closer to our goal. So now, whereas before we had 3 functions, one for each different platform, now we have one function which takes our interface and will pull that file. And you can drop in any of the things that we've just defined, and it just works seamlessly. But there's a problem. Now, in each of these implementations, they're going to be spewing back errors. So if you get your Google credentials wrong, you're going to get a Google credential error, which is going to look different from a Amazon S3 credential error. You might get a not found if you try to look at a file. So, which is going to be different from the S3 one, and it's going to be different from the one you get from os.open through local. So we need to try and simplify some of this error handling. And so we're going to push it back on the implementations and find a few standard errors to use with our interface. So like an error not found that you return when the implementation you're using gives you back their like specific not found error. Permission denied is another standard one. And because we're doing lots of things over the network, it's going to be quite common for things not to be available. We should be expecting this. We should actually deal with it as well later on. So we need to know about this. That's probably the most important one. Permission denied, of course, normally means that you've really got the credentials wrong. And so that's generally a fatal error. So that's almost more important, in fact, than unavailable. But anyway, so how's the testing situation improved? Well, we only need to test each one of these implementations now once. It doesn't have to care about any of the other code in any of the process or program that you're doing. But we do now need to check that we conform to this extra standard we've just set, that the errors, the correct errors for things going wrong are actually coming out of our various implementations. But if we write some code that uses an FS interface, how are we going to test that? It's actually really, really simple. Because we have an interface, we can just construct whatever object we like to behave like whatever file system we like. And in particular, this one, a simple memory-based file system, is just a map. So you put files in here by assigning a path to the byte slice, which is just the contents of the files. And then the open method simply, if it's there, it returns you it as the recloser. And if it's not there, it just says error not found. So this is great. It turns out actually later on that this is very, very useful. So keep that in mind. So what's next? Well, we have an interface. So let's see what else we can do. So a common problem that we certainly had is that we had a set of files which were distributed in multiple places. So like, AWS, cloud storage, local systems, like local shared network drives. And we want to be able to hit all of them in the case, or at least hit more than one in the case that one of them isn't working. Normally, when you're writing this on an individual level, it's a real pain. But now I've got this interface, we should be able to make it better, right? So it's actually really, really simple. You define a new type, MultiFS, which is just a list of file systems, and you go through them one by one until it gives you the file back. The new MultiFS is just like a little bit of sugar, so you don't have to bother writing lists. But this is incredibly simple for what it does and what it allows you to do. And it's also incredibly simple to test. And so now let's just use it. So we have, let's say we have a bucket in S3, something in Google Cloud Storage, and we have some scratch space. This new file system, which you can pass to your programs that take file systems, will now do a lot of work for you. And the program won't know the difference. It just doesn't care. It wants the file. And you've just moved all of those problems way up front. And this is exactly what we were looking for. But what if the source of the file is actually a web server? I don't know how many of you, there's a geodata service, and they give you a web URL. You can download their new IP geocoding data from there. We had this a few weeks ago, actually. And so what we actually need to do was put it into one of these chains. So why not? This is really easy, right? So you can implement an HTTP file system, essentially. With the root is the root of the URL, and then the file system is just all of the paths that you're going to allow access to on the right-hand side there. And it's really straightforward to map the errors through. So now our chain looks like that. And we haven't had to write any specialized code for fetching files, putting them on the local system, and then using them by something else. It all just pieces together really nicely. So I mentioned before about this error unavailable. Like when this happens, you almost certainly want to try again. But now that we have an interface, we're in a situation where you only ever have to write the code that tries again once. And this is exactly what it looks like. You can be more clever in how you allow things to cancel. I mean, I'll get on to some of that later on. But essentially, this is it. You just say how many times you want to try and how long you want to wait between each attempt. And so this just wraps your file system, whatever it was, network, and performs all this for you automatically. So now, in our multi-list that we had before, if any of these are flaky, it's not a problem. If a region goes down, it's not a problem. It's already in the code. You don't have to start like changing config files, pointing stuff different places. It all fits in really nicely, and you haven't changed any of the rest of your code. So another problem that we had that we wanted to try and fix was namespacing. So when you have a process, particularly if you're serving user data, and each user has their own file, their own folder in your bucket or in your storage system, and then their data is inside that, you end up passing around paths, file paths, and at every point you have to check and then concatenate something to the file path. Okay, so I'm this process, I have this bucket, and then I'm going to add the user's paths to that, and then the file that they want at the end. And this is just a huge mess. It's very hard to test, for one. But instead, you can use another wrapper around a file system, which will automatically add something to every single path that you put through it. And so now the namespace is baked into the code, not into a string that you're passing around. So every time you pass a file system to a function, it knows that it can just write to the root of that file system, because the thing that gave it, the thing that was giving it the file system has set it up so that it can just write, well, I guess in this case, read, sorry. Spoilers for what happens later on. So it can just read from that space, and it owns that space. All right, so I have a demo. It's going to be interesting because I have to. All right, so actually, I'll just close this, sorry. So what I've done is I've created a simple HTTP server. You send it a request that looks like this. So you send it a JSON struct with a path in it, and it uses the file system that it has defined in it to look up that file, and if it has it, it'll return it. If it doesn't have it, it'll return an error. Okay, so I have conveniently set up a little file tree on my local system because I didn't want to trust that any networking was going to actually work. Oh, does it need to go up? Sorry, guys. Actually. Is that better? All right, now. Okay, I'll stop messing that up. Oh, so many pixels. All right, so let's run this again. So I would take bets on this, but I was doing it earlier and I managed to confuse myself. So let's go through it slowly, and there's a good reason for this. It's confusing. All right, so I started this demo server, and what I have here is a memory file system with a single file, hello world, with the text hello world in it. Let's close this so I can show you. I have a local file system, which is conveniently pointing at that directory I just opened. And I have a prefix file system, which is going to stick a Gopher prefix on every single path I pass through it. All right, let's run it. Yeah, something I prepared earlier. Let's just ask for a random file. Not found. Seems to make sense. All right, it looks as though it's working. So what else is in my tree? So I have this example txt, which should be exposed by this local call here. All right, works. Oh, I should, just to prove that it works. Should I move this up again? All right. And then also, we have this SID file in here, which should get hit because of the prefix. All right, that worked. Right, so this, let me just show that it worked. All right, so it turns out that although this is very convenient for building file systems, it's really confusing when you try to debug or anything goes wrong. So clearly, we just have all these file systems everywhere, and we don't know what the heck's going on. But we can fix it by making the problem worse, creating more file systems, of course. But they will help us to work out how this all fits together. All right, so debugging and tracing. We want to be able to record file system calls and pick up errors without having to go through all our code and put log statements everywhere. Yeah? Have you done this? It's frustrating, isn't it? Because especially if you screw up the log statement, and then, yeah, anyway. How many of you guys have used the trace package? How many of you guys have heard of the trace package? Keep your hands up if you think it's awesome. Why did you put your hand down? All right, sorry. Who's heard of the XBAR package? And who's used it? Awesome. You're going to have a treat, those who haven't seen it. All right, so Logging. Again, we create a wrapper. It's easy. So we're going to log a call every time it comes in. If there's an error, we're going to log that as well. It's pretty simple. We put a name in here just so that on the log you can actually see which file system is doing what. Tracing, it's the same story. It's exactly the same story. I'm going to actually do a demo of this. So something that has sneaked in here is this context, which has to be there for the trace to work. In fact, like I've simplified all of this. Well, this is the only simplification I've made just to make it easy to start. But this allows you basically to pass information about the request that you're following through the system, rather than it just being a file call with a path. Okay, and finally, we're going to use the Xfile package to count some statistics. So this will give us live stats on what's going on in the file system, what's erroring, and yeah, basically how much is being accessed. So again, this is just a simple wrapper. We give it, Xfile allows you to publish variables. And what I mean by publish is you set values to them and they sit in memory. And then when you make a call to the debug server, which is an HTTP server that you run on your box, it prints a JSON, it prints out JSON of all of those values so that you can see it in real time. It's a way of pulling data directly from your process without having to ever push anything, as you do with things like statsd, you're pushing stuff all the time. So this, I define a map, and I'm wanting to count the numbers of a particular error that comes through. This turns out to be quite clever because you can count the error nil, which tells you how many successful calls you have, and then you can count all the other specific errors to find out, how many unavailables, not founds, permissions denied. When you have a lot of permissions denied, it normally means you've deployed something with the wrong credentials, and you should immediately roll back. We found. So let's do a demo. Now, this looks horrific, but it really isn't. Trust me. So all we've done here is set up a debug function, which takes a file system and a name that you want to use throughout all of this debugging info to know what's going on. All right, so we're going to do logging, we're going to do tracing, and we're going to do stat counts on error not found, because that happens to happen a lot on a local file system, and on nil, which is the call finished successfully. All right, so now I've modified the file systems down here to each have this debug wrapper. So you'll be able to see everything go through. So let's run this one. Okay, so it says it's starting the debug server, which we're going to use very shortly, and the same demo HTTP server, conveniently on different ports. And right, so let's hit a file. Okay, exciting. We've got some information. So this is basically tracing through everything that the system is doing to serve you a file. So it's trying, first of all, in the memory one, in the memory file system, which obviously doesn't have that filing because you can see it just behind here. It tries on the local disk, and then it goes to the prefix one, and ta-da, it's there. All right, let's just try a few. Let's just like mash it a bit. Woo-hoo. So much fun. All right. It's certainly easier than typing correct names. All right. And let's keep that running and just have a look at what kind of tracing information we have. So traces, you specify a trace in your code, and so all the events appear under that as separate events. And so these are the mostly unhelpful queries I just made. But actually, they are very, very interesting. So you can expand them out. And if you remember, we were wrapping every single call. So you can see exactly what it's doing in the system and where it's going wrong. It's going through the multi, it's going to the memory, it can't find it, it's going to the local, can't find it. When you're in a network environment and you're pulling things from all over the world, this is like absolutely invaluable. Like once you've seen this, I'd be surprised if you ever, okay, what have I done? Okay, sorry. I'd be surprised if you ever want to go back to just reading logs that are linear and horrible and yeah, not request-based. So also in here, there was, so this is tracing for everybody who doesn't know it, hasn't used this before. I suggest you go out and look it up. It's really awesome. And so the other thing was the XVAR stuff. So this is what's being sent out by the XVAR package at the moment. So by default, it gives you useful stuff like memory stats and the command line parameter you use to execute it. That's because it's, the reason it's weird is because it's come from the presenting tool. And then everything that you set then appears here. So you can see all of these errors. If it looks like we have a serious problem, let's put some good things in here. All right. Let's go back. Yeah, Jason, random way. Okay, yeah, so these are kind of now working a bit better. Few OKs. So yeah, this is invaluable. You can plug this into your health checking system. It can immediately tell you what is going wrong, which file system is going wrong, and actually which credential you've messed up in the case of things like permission denied, or things suddenly, yeah, going offline. All right, so we made a mess and we tidied it up. So we have logging, tracing, stat counting, retrying, namespacing, multiplexing, multi-platform, and it all comes down to one little thing, which is the very basic interface we started with. All of that behavior is now available to anything that you want to, that you can implement using this. So as I kind of hinted at the beginning, we've taken this a lot further, and we have an open source package on GitHub, which is called Storage. We also do writing and deleting. We have proper cache wrappers. So when you pull a file that's not in the system that you want it to be in, it will actually cache it there for the next time you look at it. We also have a content addressable wrapper for deduping stuff, which, of course, because of the way the system works, you can run that on, well, anywhere you like, basically. So yeah, just by conclusion, interfaces are awesome. They're an amazingly simple way to create reusable building blocks. Like you have a file system, and we have a tracing system and a logging system, and a way of reporting health, and we just like merge them together in about 20 lines of code, and all of a sudden, like you can trace every single file system you have. Yeah, and if you find yourself repeating the same patterns, there's probably a better way to do it. Okay, that's the end. Thank you. Any questions? Yes. Right, yeah, good question. So the way the tracing works, which you didn't see because it actually originates in the web server when it makes the request for the file, is that you, let me just quickly show you. You might have seen it. I mean, I know I skipped through this quite quickly. Here, on the context, which is passed through every single layer, if you enable tracing on a particular context, then as it goes through, any traces will be added to. So what generally happens is you pick 10% of requests and you switch on tracing at the top level, and then as it flows through the system, it gets annotated. All of this stuff is lazy evaluated, so lazy printf. There are a bunch of other functions as well in the documentation. You can also actually mark things as sensitive, so they don't actually get written out in full. I'm pretty sure that's right. Yeah, so the package, yeah, but there is a slight performance. There is a slight performance hit, but it's actually not very much. So yeah, the package is really quite well defined. In fact, I'm pretty sure there was a talk by David Simons maybe 2 years ago here at golang-syd where he talked about gRPC and this. So I'd recommend you go and look it up if you haven't seen it. Any more questions? Yeah. Yeah, sure. So, sorry, I did. Sorry. Oh, of course. So you were asking, is this in the open source repo? Examples in the code. So there aren't many examples in the code. Although, as you can imagine, it's received quite a lot of work over the last week or so. And so we're in a much better frame of mind to start writing documentation. No, so the code is actually very, very simple. Let me. Oh, I don't have an internet connection. Moron. Sorry, yeah, but I'll put, when the slides go up, there's a link at the end. So just follow that. And in fact, we can probably get some internet to just come and talk to me at the end. If you're interested in contributing or you have like ideas to add to this, then like, yeah, we're always looking to hear from people. So any more questions? So it does happen. Most of the time, it's not the provider, but it does happen. And the system, so yeah, actually, I'm quite militant about this as well, because I really like to know. Because if it's not the system, then we're doing something wrong. And although this very nicely takes care of everything, if you set it up correctly and you have enough mirrors, yeah, it is good to know when things go, yeah, missing. But it doesn't actually happen that often. Normally, like a bogus crash or something somewhere else that's completely unrelated will prevent something being properly written. So we're more likely to get like half a file than we are to get none at all. And that's like even worse because yeah. But no, I think in terms of distributing stuff across platforms, this is amazing because whereas before you would have to like do things, you know, oh, if you're switching between regions and you're moving data between regions or you're moving data between providers, normally there's like a little window where you're R-syncing and you're moving people across one by one. We can just switch over straight away, and whoever asks for anything, they have to wait a little bit longer on the first call, but the system automatically takes care of it and just pulls it from the source. So we can also be, of course, R-syncing in the background, which is, yeah, or equivalent, yeah. So, any more questions? Yeah. I'm sorry? Oh, in more than one system? Ah, right, okay. Well, that's where the ordering comes in. So I know, yes, you do have to be very careful with things like that. And the prefix thing is almost completely reserved for, I'm a function, I've just got a file system, I've got to farm it off to something like, I'm doing something for a specific user, I'm just going to isolate it to the user's directory and give it to, you know, the thing that's loading a model or whatever it is. So having the ordering is strict enough that isn't a problem, I think, yeah. Obviously, like looking at it, it's very easy to imagine that crazy things can happen, just because when we were trying to go through it, it was quite difficult to see what was going on. But actually, in practice, it works brilliantly. It takes a little bit of getting your head around. I spent a lot of time with one of our guys, like going over it to get all the prefixing stuff right. Yeah, it can be pretty tricky when there are files everywhere. Yeah? Oh, sorry. Why are we using what, sir? Why are we using URLs?
Why you are not using URLs? Why you should use just pass? Pass doesn't have any schema inside. So we go in one by one.
Ah, right.
Storages, which is not efficient. We have like 10, 20 storages. What happens if your file will be on the last storage?
Right. So Yeah, no, sorry. So no. So this is one of the things that I struggled because the slides only allow for about 13 lines of code. So the the multi-file system here has been implemented and is actually never used. So this is more to be like, oh, you can do more stuff with this. We actually have a concurrent version of this. So we hit everything at once, and it's the first person who comes back. And in fact, it's a little bit trickier, but you can also sit in line. So this read closer that you're passing back, you can sit in the middle of that whilst you're reading data simultaneously from different people and decide which one you're going to take based on which is faster. So, and I say it's tricky, but it's one method. Again, it's about 10 lines. You write it, you test it, you're done. So all of this stuff lends itself very, very well to writing things that are very, very precise. They look incredibly dumb and simple, but they allow you, because you just build up, allow you to do some, yeah, pretty amazing stuff. I didn't mention actually all of the constructors that we have. We don't use those. It was a slide that I took out because it was a bit verbose. We actually use URLs to specify the file system, and then one method just creates you the instance that you need. So, okay, great. Thank you.